Hello everyone. So, what we are discussing is the thermal transmission characteristics through fabric. Till now we have discussed the transmission characteristics of functional textiles in normal condition, normal activity level. Now, we will try to understand how to measure the thermal transmission characteristics for extreme heat condition particularly. So, one of the methods is the thermal mannequin method. Although thermal mannequin is used for measuring the thermal transmission in normal condition, but for extreme condition where human subject is not suggested, in those applications we can use thermal mannequin. So, this is a picture of thermal mannequin. So, why do we need to test thermal mannequin? So, it is used for testing and product development. Earlier, initially it was used for building and automobile industry, for evaluation of performance of heating and ventilation system. Clothing industry also used for developing clothing with improved thermal properties, performance testing of protective clothing. When we are talking about protective clothing, we talk about the extreme condition and its uses, that improvement in clothing comfort, health and safety in working life. So, the salient features of thermal mannequins are: it simulates the human body, the whole body and the local part, and it simulates the heat exchange. Number of individually regulated body segments are there are large number, typically it is more than 30 segments, and in other methods which we have already discussed, the heat exchange is in 2 dimension, where we keep the fabric in flat condition, but actually the heat transmission from human body gets transmitted through 3 dimensional mode. So, the thermal mannequin measures the heat transmission in 3 dimensional mode. It measures the heat loss due to conduction, convection and radiation. So, which simulates the actual heat transmission condition through human body, and the mannequins are of different types. We can get different types of mannequins like walking mannequin and stationary sitting mannequin, standing mannequin. So, and mannequin we can place at different climatic condition. Whole body heat loss is determined by summing up of area weighted value. So, at different portion the heat loss, heat transmission will be known through different segment, different sensors, and depending on the area, and if we can measure the weighted average, so we can calculate the whole body heat transmission. It can integrate the dry heat loss from human body in a realistic manner. If we test the heat loss in guarded hot plate, so we will get 2 dimensional heat loss system, which may not actually simulate the real condition, which is not realistic value. The value which we get in guarded hot plate or TOG meter or any other method are used mainly for comparison purpose, but actual heat transmission we can get through thermal mannequin system. It can measure the clothing thermal insulation objectively. So, in subjective method like the wear trial technique, we can sense the thermal insulation and we can rate it by some rating scale, but here we can measure the objective value, we can get the objective value of thermal insulation. So, this mannequins can be used in different ways. The values obtained from thermal mannequins are useful for evaluation of thermal stress in environments with human body, like at extreme heat or extreme cold, where human subject sometime is actually problem, it is dangerous. In those applications we can use thermal mannequin, and human as subject can actually feel the thermal stress subjectively, we cannot get any objective value. So, in those case we can use thermal mannequin. Determination of heat transmission and thermal properties of clothing assembly. So, fabric thermal transmission, fabric as individual flat fabric thermal transmission we can measure using different techniques, but clothing as an assembly, if we want to measure the thermal transmission, we have to use the thermal mannequin. Prediction of human responses to extreme or complex thermal condition. So, that we can predict. So, getting the result from thermal mannequin, we can predict what could be the human responses. Validation of results from human experiment regarding thermal stress. So, once we test the human experimentation and we test with the mannequin, we can validate the result. Simulation of responses in human exposure to thermal environments. Now, we will discuss different other methods for extreme heat and flame protective clothing. So, there are different methods of measurement of heat transmission through fabric, and these heat transmissions are not only a particular form, it may be in a flame, may be a radiant heat, may be splash water. So, there are different techniques, we will discuss one by one, but in most of the cases we will talk about the prediction of second degree burn. Before we go into the test method, first let us try to understand what are the materials which are used for extreme heat protective clothing. Carbon fiber is one of them, which is used in outer apparel, protects worker against open flame up to 1000 degree Celsius. So, in those applications carbon fibers are used, and this fiber they do not ignite and shrink very little in high temperature. So, shrinkage is very less in high temperature and they do not ignite. So, due to this characteristic we can use this fiber for open flame and it has got low weight. So, lightweight, if we want lightweight fabric, typically for any performance clothing we need lighter weight, high chemical resistance. So, very high chemical resistance is required, high temperature tolerance and low thermal expansion. So, these are the quality which actually makes the carbon fiber is material which can be used for protection from open flame. Next fiber is aramides. This fiber, it is a class of heat resistant and strong synthetic fiber used in aerospace and military application for ballistic, body armor and composite. The chain molecules are highly oriented along the fiber axis, hence a high protection, higher proportion of the chemical bond contributes more to the fiber strength. And another characteristics is that aramid fiber, they have high melting point which is more than 500 degree Celsius. So, we can use this fiber for high temperature application. Kevlar, when it is woven, Kevlar forms a strong and flexible material. The initial degradation temperature and maximum degradation temperature, they are actually the rate is that 520 degree Celsius, it is the initial degradation temperature and 8.2% per minute in air, and it can resist 450 degree Celsius for few minutes. And if we keep this fabric made of Kevlar at high temperature as high as 250 degree Celsius, it can maintain its strength at least for 1 month. So, Kevlar can be used for high temperature application for longer time. Nomex is one fiber which is very commonly used for flame protective clothing. It is known for their combination of heat resistance and strength, do not ignite, melt or drip, better long term retention of mechanical properties at elevated temperature. So, at high temperature it maintains the mechanical property. The fiber is inherently flame resistant, it does not melt, but it decomposes at 400 degree Celsius. So, although it does not melt, but at high temperature like 400 degree Celsius, this fiber decomposes. So, we can safely use at high temperature which is less than 400 degree Celsius. And when this fiber is exposed to flame, the unique quality of this fabric, unique characteristics of this fabric is that it swells and becomes thicker. So, once we prepare fabric made of Nomex and it is exposed to flame, the fiber itself swells and it becomes thicker. So, we can see here. So, this is a fabric made of Nomex, okay. And this is being heated. Heat is being applied. Once it is heated, this fibers or filament will become thicker, and as it is this filaments are thicker. So, this open pores will be blocked due to swelling of the fiber, and as this openings are blocked, this will enhance the protective performance. The heat flow through open space, the radiative heat flow through the open space will be much higher than the compact film. So, when exposed to flame, it swells and becomes thicker, forming a protective barrier between heat source and the skin. So, this protective barrier stays until it cools. So, once it is cooled down, again the openings will be created. So, that will give the breathability, but when it is exposed to the flame, when we require protection, and this gives extra protection, extra few seconds of protection it will give, which will prevent from burning. This is one of the unique characteristics of Nomex. Now, international standard for fire protection, which is National Fire Protection Association NFPA, which is followed worldwide, and the standard on protective ensemble for structural firefighting and proximity firefighting are evaporative heat transfer through garments, thermal insulation, durability of barrier material, radiant reflective protective area of proximity fire fighting, and this NFPA involves in designing, performance and testing and certification. So, designing, performance testing and certification, all these activities is done by NFPA, and there are standards available in NFPA 1971 and 1994. And now, if we want to classify the thermal environment, this can be classified in 3 different exposure. So, first is that it is a routine exposure, where the firefighter operating hose or fighting fire from a distance. Okay. So, when the operator is fighting fire from certain distance, where threat is not that much severe, the air temperature is not that high, 60 to 100, which is called routine exposure. The heat flux is from 8.83 to 1.67 kilowatt per square meter, and we can have very high tolerance time, and in this routine exposure we do not need any special clothing. Okay. But relatively hazardous exposure, situation outside a burning room, which it is not inside the room, outside a burning room, or firefighter ventilation of ventilating a fire without water. Okay. So, that in that case the air temperature is considered to be 120 to 300 degrees Celsius, the heat flux is higher than earlier 2 to 12.5 and tolerance time is less, where a firefighter can stay there from 1 to 10 minutes, and turnout uniform is necessary to avoid any burn injury. No special clothing is required, but some uniform is required. But in case of emergency situation, that is situations encountered inside a burning building, that type of situation is required by firefighter. The air temperature, it is ranging from 300 to 1200 degrees Celsius, the heat flux is from 12 to 200 and the tolerance times will be from 5 to 20 seconds. So, in emergency situation we need special thermal protective clothing. So, this thermal protective clothing is not normal. So, we have to have very special clothing. So, the type of burn injury is that the burn depth is measured depending on the severity. The first degree burn is that the skin becomes red, no blister formation, and which will be actually a person will be recovered after few days, it will be recovered. And the second degree burn, the skin blister, epidermis must regenerate. So, the epidermis will be regenerated and this can be recovered, okay. And in most of the cases we can go up to this second degree burn, okay. We can predict, and beyond the second degree burn, which is called third degree burn, full thickness of the skin is destroyed and skin cannot be regenerated, okay. Scar formation is there. So, that situation should not be actually reached. Before that we should be able to come out from the fire condition, and the time required for second degree burn is extremely important, and that is actually measured for by the different instruments. So, that is the measurement techniques, and the construction is that most of the firefighter clothing, they have 3 layers. The outer layer, which is thermal protective or reflective layer, this is outer layer, and middle layer is moisture barrier layer. That means, it will not allow the water molecule to come inside, but the moisture vapor it will allow to pass through that. So, whatever the sweat, whatever the moisture generated in the human body, it should actually get transmitted through this barrier, and innermost layer which is thermal liner, which is actually which protects the fabric, which protects the human body from the heat exposure. It is mainly the insulating layer. So, if you see with this schematic diagram, the different layers. So, multi-layer structure of protective clothing and skin. This red source, it is a external radiative heat source. So, ambient air where external radiative heat source, it may be any radiative heat source, may be flame, may be fire, any heat source, and this gray part it is showing the protective clothing. So, protective clothing has got 3 layers. So, outer layer, outer shell, moisture barrier layer middle and thermal insulation, and in between these layers the gap which is air gap is created, which also helps in providing the insulation, and this portion it is called the microclimate, air gap between the clothing and the skin, and the left portion this is actually the human skin, epidermis, dermis and subcutaneous tissues. So, from there we can predict the heat transmitted to the epidermis, which will be actually which will result the second degree burn, and we can predict the second degree burn time. So, there are different test methods for extreme heat protective clothing. So, these test methods are, first is that flame exposure test. Flame exposure tests are of 2 types. One is that with horizontal orientation of fabric, another is vertical orientation of fabric. So, flame exposure test with horizontal orientation of fabric, here the fabric is exposed with direct flame and the heat transmission and second degree burn time is recorded. Next is that radiant heat exposure test. Here the heat source is that radiant heat. Earlier case it was the flame, in this case the heat source is the radiant heat, okay, and the fabric is exposed to that radiant heat and the amount of heat which is transmitted through the fabric is measured. Next is called hot surface contact exposure test. The radiant heat exposure test was not in contact. So, this is a fabric specimen clothing and the radiant heat, there is the source which is not in contact with the fabric, but in this hot surface contact exposure test is that fabric is exposed with a hot surface. So, hot surface is in touch with the fabric, and then the amount of heat transmitted through the fabric is measured, and the second degree burn time is calculated. Like this is my clothing and some hot surface is in touch with the fabric, okay. So, hot iron is in touch. So, how long will it take to have second degree burn is measured using this type of test, and radiant heat, that means the radiant heat source is not in contact. Next method is that steam exposure test. So, after hot surface or radiant heat exposure, suppose this is the fabric, now I am wearing this clothing, some steam is coming out, okay. Sometime it happen. So, during the steam, so I may get actually injured by the heat injury, and this level of heat actually transmitted through the fabric due to the steam exposure is measured in this test. Next method, it is hot water splash exposure test. Now, sometime it may happen the fabric is there, hot water is being splashed on the fabric and the level of protection the fabric will be given is tested by this method. Another method here, it is a hot water immersion with the compression exposure test. Suppose the fabric, the person is actually jumping inside hot water. So, how will it actually transmit the heat from the hot water to the skin? This test method will measure. And last method, as I have mentioned in the first method, it is a first method, it was the flame exposure with horizontal orientation, and last method is the flame exposure test with vertical orientation, where the fabric orientation is in vertical condition, because in most of the application we have seen the fabrics are in vertical condition. So, in this test we can measure the flame exposure, the heat transmission through fabric in vertical orientation condition. So, all these test methods, the unique purpose of these methods just to measure the heat transmission through the fabric and to predict the second degree burn condition. And in all this process, all these methods, the heat is being supplied in one direction, one side of the fabric, one surface of the fabric, and from other surface of the fabric we actually record the heat transmitted. Now, first, which is called flame exposure test. Here the components are: A, it is a gas burner which actually produce flame, and C is the specimen support frame, and the fabric B is actually fixed on specimen support frame, and other side of the fabric is actually exposed to the flame from the bottom, and fabric is placed in horizontal condition, and on other side of fabric there is the skin simulant sensor. There is a sensor, heat sensor, which is actually representing the human skin. Now, once the flame is exposed, the fabric is exposed to the flame, the heat will be transmitted through the fabric, and the skin simulant sensor will sense the, will measure the heat, and it will actually measure the time required for second degree burn. The fabric specimen of size 10 by 10 centimeter, the 10 centimeter by 10 centimeter square fabric is mounted above the burner using specimen support frame with the outer layer of the fabric system facing the burner. Okay. So, one layer is facing the burner. The fabric specimen is protected from the heat source before and after test run. So, before and after test run, the fabric specimen is protected with some shutter arrangement. At the time of the test, the burner is placed beneath the fabric specimen, and the flame is delivered for a time that depends on the structure of the fabric. Now, if the structure of the fabric is thicker, if it is thicker fabric or very compact fabric, then flame exposure time will be high. So, depending on the structure of the fabric, the flame exposure time is changed, okay, and level of frame is also changed. The thermal energy transferred through the fabric specimen is processed using a skin simulant sensor mounted on an insulating board. Okay. So, on an insulating board a skin simulant is mounted and which is located just behind the fabric specimen. In one side the flame exposure is there and in other side it is a skin simulant is placed. The surface, that is the epidermis of the skin, that the simulant surface, the surface temperature of the sensor is recorded and the second degree burn time is calculated. So, that skin simulant, it records the surface temperature and the time required to reach the second degree burn time temperature, second degree burn temperature, that whatever time it is reached, that is calculated and it gives the thermal insulation of the fabric in terms of the second degree burn time. The next method is that the same method which we have developed in our laboratory here, which is the experimental setup, which is the flame, direct flame exposure using horizontal fabric alignment. From the bottom of the fabric specimen, the flame is exposed, as the fabric is exposed through the flame, and on other side it is the skin simulant is there, the heat sensor, and the computer records the temperature increase, the level of temperature increase with the time. Okay. This is experimental setup. Here the gas, propane gas we normally use here, and which is with the controller which controls the level of flame, and there is a shutter. After the removal of shutter, we record the time and the computer records the level of heat exposure, heat transmission and the increase in temperature. And we use the Stolz curve to predict the second degree burn time. So, this is the response, okay, and Stolz response curve, it is shown in the red color, and the sensor response is in black color, and at this point when it is intersecting, this point which is as per this picture, it is a 8 second. This means thus at 8 second it reaches the second degree burn. So, that means the fabric assembly will have the second degree burn after 8 second. Okay. Just to compare the burn prediction with the Stolz criteria. Next technique, which is radiant heat exposure test. Here the fabric specimen, which is B, placed in horizontal direction. A is the source of radiant heat. Here it is a lamp, radiant heat lamp is there, heat source, and C other side it is a skin simulant. So, from top the heat is exposed, then the fabric is placed, the radiant heat passes through the fabric, and on other side skin simulant is kept, and in like earlier case, here also skin simulant will receive the heat from the radiant source, which is actually transmitting through the fabric, and the data is recorded and processed using special software. In the modified ASTM E1354 test, heat is generated by the truncated cone shaped electrically heated coil, adjusted to deliver a heat flux of 84 kilowatt per square meter. That is the amount of heat which is required for second degree burn, okay. And the heater is 5 kilowatt 240 volt. Okay. The specimen of the fabric system, that is 15 by 15 centimeter, which is placed horizontally mounted beneath the heated coil. It is placed just below the heated coil, and the heat flux is kept uniform within the center, that is 5 centimeter by 5 centimeter area of the specimen. So, total area of the specimen is 15 centimeter by 15 centimeter, and at center at least with 5 centimeter by 5 centimeter area, the heat flux should be kept uniform. Okay. So, that uniform, that, and below that area the skin simulant is placed. A transverse shutter was used to protect the fabric specimen from the heat source before and after test. That means, the heat source, the light electrically heated coil, it is actually it starts releasing heat, but the shutter is placed. When we need to measure, when we start recording the time, that time we remove the shutter, okay, and after the test, to protect the fabric we close the shutter, so that the extreme heat does not transmit through the fabric. The radiant heat exposure time for different fabric specimens is varied according to the structure of the fabric. So, radiant heat exposure time will be high for thick fabric and vice versa. For thin fabric we can expose with the shorter time. A skin simulant sensor attached on the frame is placed behind the test specimen, just below the test specimen, to process thermal energy transferred through the fabric during the exposure. So, it records the thermal energy which is transmitted through the fabric, and this surface of this skin simulant, which simulates the epidermis of the skin, the surface temperature of the sensor is recorded, and the second degree skin burn time is calculated using customized and programmed software. So, this customized software was also used for flame. Here also for radiant heat exposure we can use some customized programmed software. So, we will stop here, we will continue with the measurement of heat transmission in extreme heat condition in next class. Till then, thank you.